Our next session will be a tech demo by the president of Agility Robotics, Damion Shelton.
Okay, so by way of intro for this talk, I wanted to have a message for any investors in the audience. So about 6 years ago, when we were first really looking at using reinforcement learning with robots, my co-founder Jonathan was very frustrated because every time I hear somebody say reinforcement learning, what I hear is math. And so if you substitute math for reinforcement learning, his theory was that the pitch would be more honest. The environment that we're now in is if someone says deep reinforcement learning or reinforcement learning with human feedback, it means hard math. And with LLMs or other generative AI, it's math that no one understands. So with that, what I wanted to talk about, and I apologize that there's no robots here today. They were on the West Coast doing another demo, but we hope to have robots down here in June for the June event. I wanted to talk a little bit about embodied AI. There's lots of definitions for this. This is one that we happen to like, and this is our robot, Digit, where you can think about embodied AI really as the unification of hardware with machine intelligence, whatever intelligence means to you, and the ability for that to interact with the world. We like the mobility piece of this specifically, partially because of our background, but partially because, and I here can dust off a 25-year-old philosophy degree, the idea that consciousness is extended is an important part of many theories of mind, and the ability to actually be out in the world and mobile adds a lot to, I think, what we would understand an embodied AI to be. Now, all that being said, I want to do something a little bit unusual and try to convince you that AI is actually not necessary for much of mobility. And out of everybody in the room, Mark Rabert can probably appreciate this. We actually use a very similar division to what the rest of the field does. We call it semantic intelligence, which is the top level sort of world language-like description, and then physical intelligence, which is the planning layer down to the low level contact physics of the robot. And I think fascinatingly, this looks like a robot. It is not a robot. This comes out of Andy Ruina's lab up at Cornell from about 25 years ago. This is a clockwork mechanism without the clock. And so you're able to get things that look extremely natural based on first principles physics. So there's no computer, no motor, and no electricity. This is a physics first thing that happens to look like a robot. When we look at the behavior, and on the left is a guinea fowl doing about the same thing as what Digit is doing on the right. This is tissue paper. The robot has no idea that the tissue paper is there, just like the bird has no idea that it's there. And the physics here dominates the timescales that I had mentioned in the panel this morning, millisecond level timescales. With the birds, we have the advantage of knowing that neural propagation isn't fast enough to explain the fact that you can take a hard step down and recover from it. That has to be physics-based because the round-trip flight time in your neurons simply is not fast enough. Of course, Digit has wires and not neurons, so there are ways that you could try to fake this, but a lot of the built-in physics has to dominate as opposed to the AI piece of this. And so we have, at Agility, what we would call a physics-first approach. All of our systems, all the way over from Atreus, which predates the start of the company, that was at the DARPA Robotics Challenge as a demonstrator back in 2015, all the way up through Cassie, our first product, earlier version of Digit, and then the modern Digit, all share at their core somewhat similar physics, obviously very different physical instantiations of the robot. And this is the full progression, so we're now up to the imaginatively named Digit version 4. There was a V0. V0 was not very good, and so we don't show it. But we're up to Digit 4 that is actively deployed at GXO, among other partners, actually doing physical work. And so when we think about the hardware as the foundation down at, keep in mind, again, this sort of physics layer here, why is that? It's because if I just do something relatively simple, put my hand on the podium here, there are contact forces that are being exerted on my hand about 200 milliseconds before my brain is aware of it. And there are lots of problems with robots, but one of them is also that force perception problem. So to avoid breaking things, among them the robot, you have to have a way to move through space without relying totally on your understanding of the world. So it is extremely important that the hardware be by itself capable. You cannot AI enable a rock to fly, is our favorite example. Now, you can do useful work with this. This is an example that we first showed at ProMat, which is a logistics trade show about 1.5 years ago. At the time, we couldn't disclose that this was motivated by Amazon, but we shared that publicly last year. e-commerce fulfillment bins off of a racking system. There is no AI here, or at least there is no AI as anybody who's trying to sell you AI would understand it. It's done with commodity robotics motion planners that would be sort of considered state-of-the-art 5 or 10 years ago, but aren't really modern AI. And we did some live demos both at ProMat a year and a half ago and Modex. We're proud to have been, we think, the first company to ever live stream a continuous demo from a show floor. So we had this set up. This was kind of it. Our point was robots can do boring work so people don't have to do boring work. So if you get bored watching this, that's kind of the point. Now, you can do a lot more creative stuff. Keep in mind, this is still without modern AI. I'll get to that in a second. All of these kind of complicated behaviors, bin stacking, one- and two-handed manipulation, being able to avoid complicated workspaces. This is with an automotive manufacturer that we're working with where you have to be very careful to not bump things in an aisleway with this large tote. None of this, again, requires AI. So why am I making this point? It's because when you get to an AI-powered software stack, there's a whole lot more that you can now unlock on top of this because all of those behaviors don't require AI, i.e., you don't necessarily need to teach your AI how to do all that stuff. That's, I don't want to say solved, but it is solvable in terms of how robotics is done. So when we look about how at Agility we're thinking about this, the cognitive layer, and there probably are other ways around this, but the best way that we have found today to deal with this is with existing LLMs or VLMs. Those are trained on internet scale data, as has been noted by other people today. Access to those data sources in robotics is practically non-existent. In some sense, you're trying to really say, what is a podium? What is a room? And so if I tell a robot to walk into the room and up onto the podium, what am I actually telling it to do? That's solvable because humans have written down lots of words over hundreds of years about the world that we live in. So we don't have to rely on robotics training. This is not a robotics training problem. This is a human semantics training problem. By the time we're down at the bottom, though, notice that force transparent legs sort of persist across all these epochs, even as you phase more AI in. And the reason for that is you can't solve that problem any other way. The world exists. It has physicality that's not directly solvable with AI. So here's an example of using the AI reinforcement learning stack. Remember, hard math is what it's doing here. It's picking up a tote. First tote was empty. This tote has 10 kilograms in it. This was trained in simulation. And then the last one, which I like a lot, is 10 kilograms plus an additional 10 kilograms actually tossed into the bin dynamically. That was not in the training set, but the RL policy is robust enough for the robot to be able to pick it up. It drops it at the end just because we told it to put it down because we were starting to hit the joint torque limits on the robot. This is an example of something that you can make use of like from the panel this morning. This is actually work that we did do with NVIDIA, looking at using the Isaac Sim and Isaac Gym product line to train an impractically large number of robots in simulation. So this is thousands of digits done entirely in sim out of an initial population of millions of digits. And then we down select that into one candidate model. And we have a good enough mapping between real and physical world that we were able to do what was called a zero-shot transfer. So the RL policy from the simulation was copied over to the robot and was able to work with no further training or modification. Other folks have done this. We think we were the first people to do this with full humanoids, although it's possible that there are some folks who have done it and just haven't told us. So if you take those layers, and remember the RL pieces here are somewhat modular. This was also part of the work that we did with NVIDIA. This was grafting a large language model onto it, giving the robot some context descriptively, and then adding this sort of cheeky prompt where Jensen really likes to cook, I guess, as a hobby. So there were some freshly baked GPUs that had to take out of an oven. It looks like this behavior was scripted. It was not. What was, in some sense, scripted here is the fact that the robot does have available to it a menu of tasks that it can pull from. It knows how to walk to a place. It knows how to grab something. It knows, in this case, and I'll show you something that's a little bit different than this in a second, where the grasp points are. But the behavior was entirely novel. It, again, was not pre-scripted here. So that's very new, and it's very new within the last 2 years. Prior to that point, in order for you to have put together an application like this would require, at best case, someone using a set of code blocks that allow you to basically compose a set of pre-scripted actions into a sequence and then deploy that, but that sounds an awful lot like you need to hire an engineer to take GPUs out of an oven, which is probably not the most efficient use of venture capital. Moving on to something a little bit more complicated, this is from about a year and a half ago. We did this with OpenAI, and the prompt here was a voice prompt, hey Digit, clean up this mess. Now keep in mind, we separate the context of the LLM, the semantic intelligence piece, from the physics of this. So Digit itself doesn't know what a mess is, it doesn't know what cleanup is. My favorite piece of this entire demo was what it just did, which was to put the bubble wrap into the trash. Well, why did it do that? It's because in the US, at least, many cling films are not recyclable. That was emergent behavior coming only out of the LLM. Now, in this case, the world environment was preceded to it. Basically, Digit was told, hey, there are these objects in the world, and there are these structures in the world. And keep in mind also that we were able to tell, in this case, ChatGPT, what the API for the robot is. But everything else that you're seeing here was totally emergent from the demo. It was not otherwise canned. It also weirdly happened to work on the first try, which I've been in robotics for 25 years. Very few things work on the first try. So moving on, you might then say, well, what does it look like if you get into a more complicated case where you do not pre-script stuff? So this is the Claude VLM from Anthropic. And this is going to be a little bit less impressive from the outside because you're actually looking inside Digit's head and seeing its thoughts and also seeing what the cameras are seeing. In this case, it is actually looking around. The motion of the robot and the ability to capture images is under control of the Claude LLM or VLM here. And it's able to actually do things sort of similar to what we showed with the ChatGPT, and is having these little thoughts like, hey, this looks like a low confidence view, so I'm going to try looking around and see if I can get a better angle on it. That internal dialogue is a really interesting observability improvement over where I think some of the state of the art has been until quite recently. And again, this was done a very similar way. Basically, we taught in air quotes Claude the API for the robot and then exposed it. So that's kind of what you can do with this approach. Now, more recently, and this is stuff literally from the last week and a half, so we haven't shown this publicly yet, you can get into totally greenfield control of the robot. On the left, this might look like a relatively simple case, but this was asking a VLM that we had no training control over, but where we had worked to integrate some of the API, where the grasp points were on a close hamper. I had never seen this close hamper. In fact, if you're very observant, that is not grasp points. That is duct tape that we stuck on there to see if it confused anything. And so it just decided that that looks like handles, so it picked it up. We just did a demo out on the West Coast actually yesterday afternoon with this, where we can actually look at and categorize laundry. I am not bullish on the robot butler market, for the record, but it does make an interesting demo. And in this case, we're characterizing it. So what are we doing with this? Well, the major thing that we're looking at right now is how do we combine that kind of VLM with our start of working on diffusion policies for the control of the robot. So diffusion policies, if anybody's pitching to you that they're doing, training data by teleoperation, this is the only thing that I'm showing you today that was teleoperated. Everything else was full autonomy on the robot. In this case, we are training sort of candidate behaviors using a very small training set, an afternoon of engineer work, doing some teleoperation to show a behavior. And before I click over to the next slide, I'll say that this is not necessarily different than other ways of giving the robot candidate behaviors. You can do very complicated math that no one understands. You can do very complicated math, or you can do just math. All of them yield behaviors at some level. And in this case, diffusion policy is fancy, and you can get VCs to give you money if you say diffusion policy. That might be harder than if you say math, but it really is, at the end of the day, a set of behaviors that the robot knows how to do. So the next image, before I pull it up, we do GoPro filming of everything that we do in the office, because you never know when you're going to capture something interesting. And this was the first time that we were able to tell Digit to do something that had no idea what it was doing, had never seen before, and where there was no environmental pre-scripting. You can see the person on the right clapping because this also worked on the first try. So what we did here was actually go get a plastic bin out of our break room and some chips. It had never seen plastic bins, never had seen the chips, and we were not otherwise pre-seeding the environment. And this was using Gemini along with some of our custom control stack to go through and actually respond to a voice prompt and do a totally novel task that never appeared in the training set and where there was no other trickery involved here. The robot is standing there. There was no teleoperation. So this is super exciting. If I had to say something that I think is really, really different moving forwards, is this sort of thing is the future of robotics. Now, keep in mind, we got here via a route, and I think why this works so well is that we don't need AI to keep the robot up, we don't need the AI to keep the robot safe, and we don't need the AI to make the robot economically interesting to customers. This is now an unlock on the diversity of tasks, which I think is the future of robotics. And with that, thank you.